Okay, now the second law of thermodynamics addresses questions about spontaneity in terms of a quantity called entropy. Entropy, we're going to give a variable of capital S, is simply the thermodynamic value that quantifies, it gives a number to the randomness or disorder of a system. The SI units of the entropy are given in joules per Kelvin. Now, enthalpy had units of kilojoules. So be careful with that, because we're going to be dealing with equations that have entropy and enthalpy in them. Entropy is generally given in joules per Kelvin and enthalpy in kilojoules. And just like enthalpy, it is a state function. So the change in entropy is a state function. All we have to worry about is the final and initial values. Now, the second law of thermodynamics states that the total entropy of a system plus its surroundings, so in other words, the change in entropy of the universe, if the change in entropy of the universe is positive, if it increases, it's going to be a spontaneous reaction. Now, the problem is the way the second law is written here is useless to us. We're going to be able to calculate the change in entropy of a system, but we will never be able to calculate the entropy change of the surroundings. It's too much. It's everything else, right? So the way this is written right now is useless to us. We're going to have to rework this so that we can determine whether a reaction is spontaneous or not. And we're going to find out that we're going to need both the enthalpy and the entropy change of the system to be able to determine that. But we're going to derive it from this idea right here, okay? Okay, now let's just come back to phase changes. So we already talked somewhat about phase changes, right? If we go from a liquid to, if we go from a gas to a liquid, we called that condensation. It was an exothermic process, which sounds weird, right? Condensation is an exothermic process. But think about it. The gas molecules have a tremendous amount of energy. They're able to overcome their intermolecular forces and not stick to one another. So we have to take that energy away, negative, right? Negative, exothermic. We have to take that energy away until the energy, the thermal energy, the energy of motion, is less than that of the intermolecular forces. Once that occurs, the intermolecular forces are able to hold on to the individual molecules, and we form a liquid. Now, these liquid molecules still have enough energy so that they can move around, but they're not escaping out into the gas phase, okay? The entropy is also going to be negative. Remember, entropy is a measure of disorder. In the gas phase, the molecules are extremely disordered. They're very far apart. Now, all of a sudden, we're putting them very close in a room. It'd be like if I ask you guys to stand up and walk, let's say we were actually in a classroom, and I ask you guys just to walk around randomly all throughout the classroom. And then I said, well, I want you all to go stand in the corner. You can still move around and bump around. And which one would be more disordered? Well, that would be you walking around freely around the room, right? So the entropy is going to be negative. We lose some chaos. We lose some disorder. And of course, going the opposite way is just going to be the opposite. We're going to have to add energy to the molecules within the liquid. So it's going to be endothermic. Adding those energies will allow the molecules to overcome the intermolecular forces and escape into the gas phase. And again, we're going to go from something that is relatively ordered to something that is disordered. So our entropy change is going to be positive. We gained disorder, okay? We could do the same thing, going from the liquid to the solid, which is freezing. Freezing, again, is exothermic. These molecules still have enough energy, not quite to overcome the intermolecular forces, but enough that they can move around. And then once we move that energy, and then the intermolecular forces totally dominate and don't allow the molecules to move around anymore, we had to take away that energy. And again, this is disordered, and then all of a sudden it becomes more ordered. So the change in entropy, again, we're going to lose disorder. So the entropy change is going to be negative for freezing. Okay. Now melting, also called fusion, right? So melting is fusion. Again, we're going to have to add energy. That's going to allow the molecules to kind of overcome the intermolecular forces enough that they can move around but not escape. And again, it's going from something that's very ordered to something that is disordered. So again, we're going to lose entropy. So the change in entropy is going to be negative. Okay. And of course, then we have things like sublimation, where we go directly from a solid to a gas. So again, we're going to have to add energy. And can anybody tell me what the value of this would be in this generic system? Because I can tell you that you won't find this value in a book. So how could you calculate this value, the enthalpy of sublimation?
Could you do the fusion plus the vaporization?
Exactly, right? Remember, we talked about this in Chem 110. We talked about the fact that we simply would add, if we're going from here to here, and since it's a state function, it didn't matter if I took this path to here and then to here, or if I simply went from here to here. They're the same. So to find the enthalpy of sublimation, you just add the enthalpy of fusion plus the enthalpy of vaporization, and that would be the enthalpy of sublimation. And then again, we're going from something that's very ordered to something that is very disordered. So the change in enthalpy is also going to be positive. And again, we can get that from the enthalpy of fusion plus the enthalpy of vaporization would be the enthalpy of sublimation. And then going back down from a gas to a solid, which is also called condensation, but I would rather use the term deposition, not to confuse it with this one, okay? Again, we're going to take away a lot of energy, so it's going to be negative. It's going to be endothermic. It's going to be the sum of the enthalpy of condensation plus the enthalpy of freezing. And again, we're going from something that is very disordered to something that is ordered. So we are losing disorder. Therefore, this is going to have a positive entropy change as well. Any questions with that? Everybody good? Okay, next. I think this is what you were referring to. Basically, this is how we can quantify the entropy change. Now, this is Boltzmann constant. Boltzmann's constant is nothing more than the molar gas constant divided by Avogadro's number. Okay, so that's all this is the molar gas constant. And it's got a fancy name. We call it the Boltzmann constant because that's who came up with this whole idea. The W is simply the number of ways in which you could change something. So it is the choices that you have raised by the number of particles you had. So let's say it's a coin, right? So a coin, you either have a heads or tails. So that would be 2. And if you have 2 coins, you would raise that to the second power, which means you would have 4 choices. You could have them both heads up. You could have them both tails up. Or you could have 1 heads up and 1 tails up, or 1 tails up, 1 heads up. This is probability. Okay, so this is probability. Okay, that's exactly what this is probability. So again, you can see that if I have a coin and I have 3, so in that case, I had 4 choices. Well, the more choices I have, the more disordered a system can be. Okay? So again, if I had 3 coins, well, that's 2 choices raised to the third, that's 8 choices. So you can imagine going down how you could have all 3 coins heads up, all 3 coins tails up, the first 2 heads up, last one, the first 2 heads up, last one tails up, the first 2 heads up, the last one tails up, so on and so forth. And if you actually do it, you'll find out that you have 8 ways to place those coins. Okay? So again, it's just, this is coming from probability, and it is just saying what are the different probable ways that you would have it. So again, this is the entropy for a chemical system. Okay. Okay, now, like I said, the Boltzmann constant is just coming from the molar gas constant. So it is the molar gas constant in terms of that 8.3145 joules per Kelvin per mole divided by Avogadro's number, which would give you a Boltzmann constant of 1.38 times 10 to the negative 23. Okay. Again, not asking you to memorize this number. You already know the molar gas constant. Okay. And I'm not going to ask you to use this on an exam. Okay. So, so there it is. And the Boltzmann constant, again, just like the molar gas constant, comes in a whole bunch of different types of units, which obviously then cause the value itself to be different. Still the same. They're the same numbers. They just have different units. And the same thing is true for the Boltzmann constant, although this is probably the number that you will see most often for the Boltzmann constant. Okay, so this is where the idea of entropy comes, okay? Is the probability, the number of different choices that you could possibly have. Okay, so if we look at the entropy change, and all we're looking at is a change in volume. The number of moles isn't changing, the temperature isn't changing, so the only thing that's changing here is the volume. Now, again, we can think if we have a volume, if the volume, let's say, increases. So if the volume increases, do you expect del S to be positive or negative? If the volume increases, without looking at your notes, if the volume increases, do you expect the change in entropy to be positive or negative? Do you expect to gain disorder or lose disorder if the volume increases? Think about all of the students standing in a room. I make you stand in a small volume. Then I allow you to explore a much larger volume. Did the disorder...
You're going to lose order?
You're going to lose order by going from a small volume to a large volume. I keep you all in a corner in a small volume of the room. Then I allow you to walk throughout the entire room, a much larger volume. Did you gain or lose disorder when I let you go from a corner to the whole room and wander around aimlessly?
We gain disorder.
You gain disorder, right? It becomes more disordered when you go from the corner where you're all huddled together to walking around the room randomly all over the place. So by increasing the volume, we expect del S then to be positive. So when the volume increases, entropy is going to increase. Now remember, we can relate this to pressure, but they're inversely related. So if the entropy change, again, this is the number of moles, okay? It's an extensive property, just like enthalpy, okay? So it matters how much. This is just the molar gas constant, 8.3145 joules per Kelvin per mole. And then this is our change in volume. So if we look at this in the change of pressure, and since they're inversely related, this is just going to be the initial pressure divided by the final pressure, right? So it's just going to flip. So the reality is you only need to know one of these equations, and you automatically know the other one as long as you know that pressure and volume are inversely proportional according to Boyle's law. You can also see that from the ideal gas law by just rearranging for any variable R, for example, okay? You can see that the pressure and volume would be inversely proportional. Okay, so any questions about that? Now, again, I stress these equations are not for chemical reactions. These are not for chemical reactions. This is simply a gas expanding or contracting. Temperature isn't changing. The number of moles of gas aren't changing. The composition of the gas molecules aren't changing. So this is just for simple expansion and contraction of a gas. Okay. Next, let's talk about the third law of thermodynamics. Now, the third law of thermodynamics is nothing more than bookkeeping, okay? But it's really important, though. The third law of thermodynamics puts a floor on the entropy. So unlike enthalpy, where we can't determine the actual enthalpy of something at a given temperature, we can for the change in entropy because of the third law of thermodynamics. The third law of thermodynamics says, okay, at 0 Kelvin for a perfectly crystalline substance, we have zero entropy. Because at 0 Kelvin, they are not moving around. There's no vibrational energy. There's no rotational energy. There's none of the types of energy that we normally think of. So the third law of thermodynamics simply says, okay, we're making this the 0 point. So that's all it does, is it's a bookmark for entropy. So as the temperature is raised, the substance becomes more disordered, plain and simple, okay? At any higher temperature, the entropy is going to be higher. Now, be careful, because we're going to find that there are some standard entropies, which I'm going to talk about here shortly. We're going to find that some standard entropies are actually negative. There's very, very few of them, but they tend to be aqueous ions. Remember that when an ion dissolves in water, it becomes surrounded by water molecules, right? We call that the solvation cage. Well, that solvation cage is pretty ordered. So that's why we could actually have a negative standard entropy. But in most cases, any neutral compound, if you heat it up, it's going to have a positive entropy, a positive standard entropy, okay? So again, the entropy of a substance is simply determined by measuring how much heat is required to change its temperature by Kelvin. Thus the units, right? Joules per Kelvin. So if heat is absorbed slowly during a spontaneous phase transition, okay, this is what I'm going to refer to as an easily reversible reaction. An easily reversible reaction. There are some easily reversible chemical reactions out there. All phase transitions are easily reversible reactions, okay? At their transition temperature, they are easily reversible, because all you'd have to do is change the temperature by a very small amount, 0.01, and you're going to go from one phase to the other. So that's why we call it easily reversible. So whenever I say easily reversible, I am simply referring to phase transitions. We're not going to worry about those other chemical reactions. We're going to assume that only phase transitions are actually easily reversible. Like I said, I'm lying to you. There are other ones out there, but these are the ones that are easy to recognize, phase transitions, okay? And that's melting, vaporization, sublimation, condensation, so on and so forth. So and again, it says the process occurs near equilibrium conditions. So in other words, it's occurring at its transition temperature. So if we're talking about the freezing or melting of water, we're talking about 0 degrees Celsius. At 0 degrees Celsius, we have an easily reversible process, okay? Now the entropy for this easily reversible process for phase transitions is given by this equation here. This equation does not apply to chemical reactions, okay? We're going to have a lot of different equations, and they're going to apply to very specific events. So for a phase transition, the change in enthalpy is just the amount of heat that's either added or absorbed at that given temperature. So this will be the temperature of transition. This will be the phase transition temperature, okay? And I said all of that already. Okay, let's try an example then. So the heat of fusion of ice at 0 degrees Celsius is 6.01 kilojoules per mole. If 1 mole of solid H2O has an entropy of 38 joules per Kelvin, what is the entropy of 1 mole of liquid water at this temperature? Okay, so basically we know that we have 1 mole of solid ice. Could I say that this ice is at 0 Kelvin? In fact, tell me what temperature is this ice at? Give me a range. Let's do it in degrees Celsius, right? 0 degrees Kelvin would be negative 273.15 degrees Celsius. So where is the temperature of this ice if it has an entropy of 38 joules per Kelvin? Can it be at 0 Kelvin, or negative 273.15 degrees Celsius. Okay, let me ask it another way.
No.
What would be the entropy if this ice was at 0 Kelvin? Actually, we can get to about, we can get to nano Kelvin. We can never reach Kelvin. It's impossible. But we can get really, really, really close. But let's say we're good and we got it to 0 Kelvin. What is going to be the standard entropy of this solid block of ice? Third law of thermodynamics. This would be a multiple choice type question, a conceptual question on an exam. 0, absolutely, right? So the third law states that if you have a substance, and we're assuming it's perfectly crystalline, okay? And so if it's at 0 Kelvin, then it has a 0 standard entropy. So the fact that this is 38 joules per Kelvin tells me that that block of ice is somewhere above 0 Kelvin, or negative 273.15 degrees Celsius. And what would be the upper temperature? What would be the upper temperature? Well, the hottest it could be would be 0 degrees Celsius. Above that, it's not a solid. Now, in this particular case, although I don't specifically tell you, I'm telling you that the ice right now is at 0 degrees Celsius. So at 0 degrees Celsius, it has an entropy of 38 joules per Kelvin. Now we want to calculate, well, what is the entropy if it's water, liquid water, at 0 degrees Celsius? So notice the temperature didn't change, only a phase change occurred. And I'll show you why this is valid here in just a second, okay? So basically, well, we know the enthalpy of fusion was given to us, 6.01 kilojoules per mole at 0 degrees Celsius, the transition temperature. So the enthalpy is just going to be that heat. We're assuming constant pressure, right? There's no reason, there's no gases being formed here. So the pressure is going to remain constant. So that means the enthalpy is just the amount of heat, right? And the temperature is the temperature of transition, or the freezing, the fusion temperature, the melting temperature. So there it is. So that's the change in entropy. So is that the entropy then of the 1 mole of liquid water? And the answer is no, right? That was the change in entropy. So the absolute entropy then is going to be that change in entropy plus the entropy it already had. Okay? So it increased by 22 joules per Kelvin. So we simply add the two. And since it was for 1 mole, we could divide it by 1 mole, and that tells us then that the molar entropy of water at 0 degrees Celsius is going to be the sum of those two, or 60 joules per Kelvin per mole. So when we look up in a table, we'll find out that liquid water has a standard entropy of 60 joules per Kelvin per mole. Okay? So again, this only works for phase transitions. No chemical reaction is occurring here. This does work for other easily reversible reactions, but they are very complicated processes that we're not going to address in this class. Okay, so why is this valid? Well, let's look at what happens to the entropy, right? So and this is what we call a heating curve. And so basically, we showed a heating curve before for the change in temperature at heating at a constant rate. So now we're heating at a constant rate, we're measuring the temperature and what's happening to the entropy as we do it. So of course at 0 Kelvin, so this is at temperature, at 0 Kelvin, we have 0 entropy according to the third law of thermodynamics. But as soon as we start to heat that solid, the molecules begin to vibrate. That's disorder. So the more we heat it, the more they vibrate. more and more disorder. So we can see that the entropy increases, the disorder increases as we increase the temperature. But then all of a sudden, as we add more and more heat, the temperature no longer changes. All the energy goes into the phase transition. So this is why we said that the del S was equal to the del H of transition over the temperature of transition. The temperature was no longer changing. All the energy was going straight into the phase transition. Now it becomes a liquid. So we see a big jump in entropy going from a solid to a liquid. Now, once it's a liquid and we keep heating it up, the temperature is simply going to keep increasing and the molecules are going to move faster and faster within the liquid. And so the entropy is going to continue to increase until we get to the boiling point where we're going to see another phase transition where the liquid goes to a gas. Again, the temperature isn't going to change anymore. We're still adding heat. We're still adding energy. But all that energy is going into the phase transition, allowing these molecules to escape each other's intermolecular forces and escape into the gas phase. Notice that that is a much bigger jump. So the enthalpies of for fusion are always smaller than the enthalpies of vaporization. Okay, it always takes a lot more energy to go from the liquid to the gas phase. Now, once they're all in a gas phase, we're going to continue adding energy to it, and the temperature is going to increase, and that means that the entropy is also going to increase. The molecules are going to be moving faster, which means that is more chaotic, that is more disorder, and therefore the entropy is going to increase. Any questions about any of that good stuff? Okay, let's talk about what are called standard entropies or absolute entropies. We don't see this for the enthalpies. Remember, the enthalpies of formation were always the change in. They were del HF, okay? These are just the standard entropies. These are absolute values. So this is the entropy for a substance at 25 degrees Celsius, 1 atmosphere pressure, and if we're dealing with solutions, 1 molar solutions. Okay, so these are absolute entropies. And again, note that the change, it's not the change in the entropy, it's the absolute entropy this time. Okay, so we're going to use the term again, del S rather, I'm sorry, just S naught rather than del S. Now we are going to calculate the change in entropies, and we're going to calculate the change in entropies from the absolute entropies. Okay, and again, the reason we can have absolute entropies is because of the third law. The third law gives us a bottom. There is no thermodynamic law that gives us a bottom for our enthalpies, and there's reasons for that. Now, just like we did for the enthalpies of formation to determine the change in enthalpy, we could use another summation law to determine the change in entropy. And it's simply going to be the sum of the absolute entropies of the products, again, going to be in units of joules per Kelvin per mole and found in the back of your textbook or in the tables of chemical data. And we're going to multiply each by the number of moles. So this is the coefficient in the balanced chemical equation. So entropy 2 is an extensive property and a state function. Okay. Then we're going to subtract from that the sum of the absolute entropies of the reactants, again, each multiplied by the coefficient in the balanced chemical equation. So again, we can see this is in joules per Kelvin per mole. This is in moles. So our change in entropy is simply going to be in joules per Kelvin, not joules per Kelvin per mole. Okay. Okay, let's try an example. Excuse me. So phosgene, now keep in mind that some of these examples are different than your notes. And that's because I've been changing all of my lecture slides to this 16:9 format and updating the slides as I go along. So same ideas, but some of the things might be slightly different, okay? Okay, so phosgene reacts with ammonia. So here's phosgene, reacts with ammonia to produce urea, okay, and ammonium chloride. So I want to know, what is the entropy change for this reaction? Now we're going to use the summation law. We're going to find the standard entropies in the tables of chemical data. So that's going to be the first thing we do. We're going to look them up. And they're going to be in joules per Kelvin per mole, okay, because we want to use the summation law. So for the phosgene, it's 283.5. For the ammonia, 192.8. Urea is 104.9, and the ammonium chloride's at 94.6. So now we can plug these values into our summation law. So we have 1 mole, right? We have 1 mole of the urea at 104.9 joules per Kelvin per mole. We'll add to that the 4 moles of the ammonium chloride at 94.6 joules per Kelvin per mole. Now that's all of our products, so we'll sum them together. Then we're going to subtract from that the reactant. So there's 1 mole of phosgene at 283.5 joules per Kelvin per mole, and there's 4 moles of ammonia at 192.8 joules per Kelvin per mole. So the moles are all going to cancel as we go along. That leaves us with joules per Kelvin. Again, we have mixed operations, so you'd have to go through and multiply. In this case, we have 4 times 94.6. That was 378.4. So that was 3 sig figs. This is exact, so this has to be 3 sig figs. Now that we're adding and subtracting, we're looking for the number of significant decimal places. The least significant is 1 in front, right? The rest are 1 behind, which is more precise. So it'll be, our answer will be 1 in front. And so our change in entropy for this reaction, phosgene reacting with ammonia to form urea and ammonium chloride, is going to be negative 571 joules per Kelvin. Any questions with any of that good stuff? So again, it's just a summation law, but this time for the change in entropy from the absolute entropies. Okay, now sometimes we could actually predict the sign of the change in entropy, even though we can't give it an absolute value, because we understand what entropy is. It's an increase in disorder. So the entropy usually increases in the following situations. First, a reaction in which there is an increase in the moles of gas. This is by far the most important of them. This will give us the greatest change in entropy. When we increase the number of moles of gas, the disorder is going to increase greatly. A reaction in which a molecule is broken into 2 or more smaller molecules. Well, that makes sense, right? If we go from 1 particle to 2 particles, well, it's certainly more disordered. And the more particles it changes into, 1 to 5, is going to be an even greater change in its order, in the increase in its disorder, right? And then finally, a process in which a solid changes to a liquid, right? Again, going from a liquid, which is kind of ordered, to a gas, which is completely disordered, or a liquid changes to a gas, okay? So again, we're going from disordered to much, much more disordered. And there's actually a third possibility too, where the solid simply goes to the gas as well. Now, both the liquid change into a gas and the solid change into a gas really, oh, I already have that, liquid or gas, really is covered by this first one here. So again, increase in the number of gas molecules is the most important thing, okay? It'll change it by the most amount. And entropy, which we called S, entropy was simply a quantitative measure of disorder. And then we talked about a few ways that we could do it. So for an expanding or a contracting gas. So for a gas, okay, not a chemical reaction, this is just a gas, we noted that the change in entropy was simply equal to NR, the ln of VF over VI. Now, when the ln value, when we take the ln of a value that is less than 1, we're going to get a negative value. When we take the ln of a value that is greater than 1, we're going to get a positive value. So in this case, I can see that if my final volume is let's say, larger than my initial volume, well, that number is going to be greater than 1, and I'm going to have a positive value. Well, that makes sense. With increasing volume, you have an increase in entropy, an increase in disorder. Again, this would be like everybody standing in the corner of the room. That would be their small volume. And then everybody running around randomly throughout the room, well, that would be a much larger volume and certainly more chaotic. So vice versa, if the volume is smaller, the initial volume is smaller than the, the final volume is smaller than the initial volume, this number will be less than 1, and our change in entropy then will be negative. That makes sense. So instead of you all running around the class, we put you all again huddled in a corner, much less chaos. So we have a loss in disorder. And then we showed, well, we know that pressure and volume are inversely related to one another. So instead of dealing with the volume of a gas, I could deal with the pressure of the gas. And it's really the same thing, except this time, since it's inversely related, it's the initial pressure divided by the final pressure. And again, all the same ideas hold. If you reduce the volume, you're increasing the pressure because the molecules are running into the walls of the container far more frequently, increasing the force. The area is remaining the same. And so again, for the same reasons, if I have an increase in volume, I'm going to have a decrease in pressure. So this time with decreasing pressure, I will have an increase in entropy. So again, they're just inversely related to one another. Okay. Then we talked about easily reversible processes, okay, also known as equilibrium processes. And the only equilibrium process we're going to talk about here is phase transitions. And for phase transitions, we know that the change in entropy, which is given by, the heat over temperature, in this case is simply going to be the enthalpy of the reaction over the temperature, since we're going to measure it at constant pressure. And for phase transitions, that's going to be the enthalpy of transition divided by the temperature of that transition. Okay. And then we also looked at the entropy change, where again we could simply determine the standard entropy change by the summation law, where we simply took the sum of the absolute entropy of the products, again in extensive values, we had to multiply each by the coefficient in a balanced chemical equation, and subtract that by the absolute entropy of the reactants, and again, multiply each of those values by the coefficient in a balanced chemical equation. So again, if we looked at the combustion, if we, excuse me, if we looked at the combustion of methane to form carbon dioxide and water vapor, again, we just look at the tables of chemical data for the absolute entropies, which this time we're going to be given in joules per Kelvin per mole. Now this time, none of them will ever be 0. So for gaseous methane, that is 186.3. For gaseous O2, it's 205.2 joules per Kelvin per mole. For CO2, 213.8 joules per Kelvin per mole. And for gaseous water, 188.8 joules per Kelvin per mole. And again, it's going to depend on the phase. We showed that, right? We looked at some water at 0 degrees Celsius, solid water at 0 degrees Celsius, and then we calculated the entropy change for the phase transition to liquid water at 0 degrees Celsius. So we've seen that both of those values were different. Okay, so again, the phase is going to matter for each. And then again, we could just use the summation law. And so the change then in entropy under standard conditions is again just going to be our reactant. So that's the 1 mole of CO2 at 213.8 joules per Kelvin per mole. The 2 moles of water, so the 2 moles of water at 188.8 joules per Kelvin per mole. And then we're going to subtract from that the 1 mole of methane at 186.3 joules per Kelvin per mole. And then the 2 moles of O2, which again, not going to be 0 this time, at 205.2 joules per Kelvin per mole. Again, the moles cancel the whole way through. So we're going to get joules per Kelvin this time. And again, we have mixed operations. So it is going to be equal to 213.8 joules per Kelvin plus our, and then so it's going to be 2 times 188. So that's 377.6 joules per Kelvin. 4 sig figs, so this will be 4 sig figs. Remember, the coefficients are always exact; they're counted numbers. Then we're going to subtract the reactant. So the 1 mole of methane will give the 186.3 joules per Kelvin, and then the 2 moles of oxygen are going to give 410.4 joules per Kelvin. So that puts these guys, again, 4 sig figs, so 4 sig figs. Plug all of that into your calculator, and you're going to get negative 5.3 joules per Kelvin. This is 1 past, 1 past, 1 past, 1 past, so this will be 1 past, and so it is negative 5.3 joules per Kelvin. So that would be the entropy change. Okay. This is number 19 from chapter 18. It says, for each of the following processes, indicate the sign of the enthalpy and entropy change. So the best thing to do is to take and put each of these into some type of chemical reaction. What do I mean by that? Well, it says metal vapor. I'm just going to call M, that's my metal. And a vapor, well, that's a gas. So it says metal vapor coats a surface. What happens when metal vapor coats a surface? What is the phase of the metal at 25 degrees Celsius? We're always going to assume 25 degrees Celsius unless otherwise stated.
It's going to be a solid.
Right. I mean, unless this metal was mercury, but we're assuming it's one of the other metals and not mercury, it's going to be a solid, right? And the reality is, even if you guessed liquid, let's say it was mercury, the del H and the del S are going to be the same. So in this case, do you expect del H to be positive or negative?
Positive?
What's that, Eugenie?
Positive.
Positive? You both say positive? I want you to think about it. Which one of these has more energy, the gas or the solid?
It's negative because we're going to the deposition, not the sublimation.
Well, no, deposition and sublimation are similar. Okay, I see what you're saying. Yeah, sublimation would be going from here to here. Deposition would be going from here to here. But again, just think about it, right? A gas has a lot more energy, a lot more than a solid. I have to take away energy to go from the gas to the solid. And if I'm taking away energy, it's going to be negative. What about the sign of the entropy? What sign's the entropy going to have?
Gonna be positive. Positive?
Positive. So it's going from, so remember, this is the measure of disorder. Is it becoming more or less disordered going from this gas to the solid?
More
It's
disordered.
become more disordered?
No. It's becoming less disordered.
Okay, so what sign do you associate with less?
Oh, wait, negative.
And what sign do you associate with more?
Positive?
Yeah, right. More is positive, right? You're gaining. Less is going to be negative because you're losing. So you're telling me I'm losing disorder, right?
Yes.
Yeah, right. So it's going to be negative. So both del H and del S are going to be negative. Okay. Ice cream melting on a hot day. What kind of chemical reaction can you associate with ice cream melting on a hot day? What is ice cream basically made out of? What is the main component of ice cream? What's the main component of you?
Water.
Water, right? And guess what? Ice cream is the same thing. You might say milk, but milk is mostly water, right? So if I have ice cream melting, what was the form of the water beforehand?
Solid.
It was a solid. And if it melts, then what phase is that water going to be in?
Liquid.
A liquid. So do you get how you could associate chemical reactions to these things, right? Okay, so now if that's the case, what's del H going to be? Taylor, what do you think? What's del H going to be for this? Do I have to add energy? Heat, right? Remember, del H is basically heat of reaction. So do I have to add heat or do I have to take away heat?
You'll be adding heat, so it would be positive.
Yeah, right? I got to add heat to melt it. And then what about the entropy? Is it becoming more or less disordered?
It's becoming more disordered.
So the sign is?
Positive.
Yep. So there we go. Okay. Okay, now we come to this one here. Can you tell me what del H is going to be for this reaction? By the way, is this font big enough for all of you to read?
Yeah.
Yeah, it's fine for me.
Is it fine? I mean, I can make it larger in the future, but if that's good, I'll leave it that size. That gives me more room to write. So what do you think? Can you give me a sign on this chemical reaction? Well, it's actually not even a chemical reaction, right? It's just the dissociation of the salt in water, the dissolution.
Is this negative?
Negative? Anybody else?
I would guess positive because it's going from solid to aqueous.
We actually talked about this in, I believe it was the first chapter we covered, right? We said some salts, when they dissolve in water, heat up the solution. Other salts, when we dissolve them in water, cool the solution down. Remember, we talked about hot packs and cold packs. So can I look at this reaction and actually predict whether it's going to be positive or negative? And the answer is no. There's no way to look at this and say del H is positive or negative. And that's going to be true on any chemical reaction. We can predict it for phase transitions, but we cannot predict it for a chemical reaction. Now, if you have some knowledge about it, like for example, I know when we dissolve salt, sodium chloride in water, the temperature of the water doesn't change. So what's that tell you about del H? If the temperature of the water isn't changing when I dissolve sodium chloride in it, what do you think the value of del H is?
0.
Very close to 0. It's not exactly 0, but it is really close to 0, right? We expect a temperature change if it's endothermic or exothermic. So if it's not changing the temperature, it's barely changing it, it's almost immeasurable, then it's going to be very close to 0. But again, you would have to know that. That's something you'd have to memorize, and I'm only asking you to memorize a bare minimum of material so that I can communicate with you. So I don't want you to memorize all those types of things. Now, what about del S? What would you predict del S to be? The change in entropy.
I think it would be positive.
It is almost guaranteed going to be positive. And why is that, Hannah?
It's going from 1 mole to 2.
Yeah, it's going from 1 particle to 2 particles. So it's going more chaotic, right? The more particles, the more chaotic. Now, I will tell you that there is another caveat. It's not as positive as you think it is. This little aqueous, well, that means that this thing is surrounded by, this thing is surrounded by a bunch of water molecules that are pretty ordered, right? In what we call a solvation shell. So this order actually kind of decreases this positive value a bit. Okay, so it's actually not as big as you might think it would be, and that's because this is actually creating order. Okay, and again, I would simply ask you to say positive because it's breaking apart into 2. But again, if you look at it and you go, why is it so small? That's why. Okay. Any questions about any of that good stuff? Okay, let's try another. This time, without calculating the exact values, I want you to decide whether there's going to be an increase or a decrease in entropy. So is there going to be an increase or decrease in entropy? What about for the first one?
Increase? Wait, no. It's gaining disorder. Wait, no, it's losing disorder.
It's losing, right? It's going from, and tell me, why is it losing disorder?
Because it went from 2 molecules to 1.
Actually, it went from 3, right? 1, 2, 3 to 1. So you're right. It lost disorder. So what sign would you associate with a decrease in entropy?
Negative.
Negative, right? So negative, and that's, of course, a decrease. Okay. What about the next one? So we've been talking about number of particles. So here I went from what, 6 particles to 3 particles, right? I went from 6 to 3. How would that affect the entropy? Am I gaining disorder or losing disorder?
Losing.
Losing. So again, that would be a decrease. Are there any other factors?
We're still going, well, you have gas in the reactants, and you have a liquid in the product, which is a loss in disorder as well.
So how many gas did we start with?
Well, we started with 6 gas particles.
So 6 moles of gas, and what did we end up with?
2.
2 moles of gas. How's that going to affect the entropy?
It's gonna decrease it.
Right. Again, and which one of these would dominate? If this one was plus and this one was minus, what would you expect the overall entropy change to be? If this one was plus, with the number of molecules simply decreasing, and this, I'm sorry, it would have been increasing, right? This would have went from 6 to 3. And then this one was the way it is, going 6 to 2. What do you think the overall sign of the entropy change would be? In other words, I want to know which one of these are more important.
The gases.
The gases, right? The gases dominate, big time dominate. So the change in entropy of this is going to be, I mean, probably in the single digits. The change in entropy of this is probably in the hundreds. So huge difference between the two. Okay, and I'm not going to do this last one. This last one is just, again, just basically the opposite of this. I don't know why I keep throwing these in here. I'll find another problem for that one. But you get the idea, right? So the number of particles, the phases matter, so on and so forth. So here we had a decrease for 2 reasons, right? It went from 3 particles to 1 particle, and it went from an aqueous to a solid. So there was that phase transition where we went from random to ordered. So for both of those reasons, we had a decrease in entropy. Okay, any questions about that? Okay, let's try another then. Okay, this says, what is the entropy change when 6 grams of ethane, C6H6, is compressed from 15 liters to 5 liters at constant temperature of 24.5 degrees Celsius? What idea or equation, what exactly am I going to do?
Delta S equals number of moles times R times ln V final and the initial over the initial volume.
Yeah, right. So all we're doing is a compressing a gas. So there's no chemistry going on here. And when all we're doing is compressing the gas, we're going to use this equation for the change in entropy. So number of moles, well, we've done that 1 billion times at this point, right? So there's the 6 grams of ethane, which is C2H6. We're going to divide that by the molar mass of methane. So in 1 mole of ethane, I'm sorry, not methane, ethane, there is going to be 30.069. So 30.069 grams of ethane. So our grams are going to cancel, and that's going to give us our moles. So that would be 0.19954 moles. And again, we could have done this all in one line here, right? But I just split it up. So there's 3 sig figs, there's 5, so this is 3. The value then is going to be 0.19954 moles. The gas constant, as we discussed earlier, is 8.3145 joules per Kelvin per mole, right? So that's just the molar gas constant, R. And then we have the ln, the final volume. Well, it went from 15 to 5, so the final must be 5 liters. And the initial was 15 liters. So we can see the liters are canceling, the moles are canceling, and we're going to get joules per Kelvin. Now that makes sense, right? We wouldn't want joules per Kelvin per mole because we're talking about a specific amount. If it was 30.069 grams, then it would be joules per Kelvin per mole. Okay. Okay, so then plug that into the calculator, and that is going to equal negative 1.822 joules per Kelvin. Let's see. So this is actually a mixed operation, and this is going to give me negative 1.0986. So this is 2 sig figs, so that'll be 2 decimal places. So now that's 3 sig figs, 5 and 3. So this will be 3. And so this is equal to negative 1.82 joules per Kelvin. Okay. Any questions about that? Again, this one, and of course the one that has pressure, which is the initial pressure over the final pressure, these equations are only ever to be used for a gas. Okay. Okay, let's try another one. So this is number 24 from chapter 18. And it says diethyl ether, which is simply known as ether, is a common solvent. So it's a really good solvent. And in fact, for a few years, they actually used it as an anesthetic in surgery. Now they quit doing that because it readily evaporated. Its boiling point is at 34.6 degrees Celsius, so just above room temperature, which means it evaporates really quickly. So even though it would put somebody under, given the inhaling the right amount of ether, ether is also extraordinarily flammable and combustible. So back in the day, they had really no other anesthetic. Before ether came along, they did surgery without anything. Maybe they gave you a few shots of alcohol, but beyond that, they'd cut your leg off, and you were there the whole time. So then they started using ether. They started putting you under. The problem is that quite a few patients died along with everybody else in the surgical room because the ether would blow up and kill everybody. So they only used ether for a few years before they switched over to chloroform. And then, of course, that progressed. Anesthetics progressed after that. But so short history on ether. I want to know, though, what is the entropy change when 0.96 moles of ether vaporizes at its boiling point? And it gives us some other information here. Gives us the boiling point in its heat of vaporization. So what equation deals with the entropy change? First off, again, what chemical reaction would we associate with this problem? What would that look like? What's happening to the ether? Is the ether changing its chemical composition at all? So if it's not changing its chemical composition, what's happening to it?
It's going from a liquid to a gas.
Yeah, right. It's vaporizing, which means it's going from a liquid to a gas. And we call that vaporization. And it told us that the enthalpy of vaporization was 27, tells us right here, right? 27.1 kilojoules per mole. So what equation or concept am I going to need to do to solve this thing? Looking for the entropy change, right? What is the entropy change? I'm looking for del S.
You do the del S over del T of vaporization over the temperature.
Say that again.
So it'd be the del S is equal to the del H, and for this case, it would be a vaporization over the over T, so the temperature.
And what is the temperature of vaporization called?
Ooh, that's a good question.
Think about it.
Is that just a vapor? No.
Think about water.
Is that
What temperature?
that boiling point?
Yeah, right. The
Okay.
boiling point is the temperature of vaporization. That's the temperature of that phase transition. So this is just TB, right? Now, this really is just del H over T for any equilibrium process, but the only equilibrium processes we're going to talk about are phase changes. So it's just going to be the enthalpy of whatever that phase transition is divided by the temperature of that transition. So the enthalpy of vaporization then is given as 27.1 kilojoules per mole. And then the temperature was given as 34.6. But we need to convert that to Kelvin by adding 273.15 to it. Okay, because again, the units of entropy are generally joules per Kelvin per mole. So on top of that, I am going to multiply this by 1,000 because again, we want it in joules per Kelvin per mole. That is the normal units of the change in entropy. So let's add this. So then this is 307.75 Kelvin. This is 1 decimal place, so this will be 1 decimal place. So we'll divide that by 307.75 Kelvin. Now we have the units that we want, the joules per Kelvin per mole. Plug that into your calculator. And we get the entropy change of, okay, I did this very differently. I'm going to have to calculate this. Okay, so 27.1 times 1,000 divided by 307.75. So that gives me 88.058 joules per Kelvin per mole. And that is going to be 2,3 sig figs. Okay, is that my answer?
No, because that's for 1 mole.
Exactly, and we only had 0.96 moles. So this, what I just calculated was actually the molar entropy change for the vaporization of ether. We want the entropy change for the 0.96 moles of ether. And we then just say that, well, that's times 88.058 joules per Kelvin per mole. Now my moles cancel, and I get the enthalpy change for that amount of ether that is vaporizing, and that's going to give me 84.53 joules per Kelvin. So that is 2 sig figs now. So this is 85 joules per Kelvin. Okay. Does it make sense that it's positive? Yeah, right. It went from a liquid, which is kind of ordered, to a gas, which is completely disordered. So we gained disorder. So yeah, it should be positive. Let's say I asked this entire question. So everything in this question is exactly what I would have given you. I would have given you the boiling point and the heat of vaporization. But what if instead of saying that it vaporized, what if I said I condensed? What if I said I condensed? So So I went from a gas to a liquid. What if I condensed 0.96 moles? What would the value be?
Should be negative
Right. And you understand why this is going to be negative.
because you're going from very disordered to somewhat disordered.
But
So you're-
how would have you actually, I agree with you, but how would have you calculated this, right? We use this up here.
Well,
So for this reaction, what is del S equal? What is this phase transition? Gas to a liquid.
that's your condensation, right?
Right, that's condensation.
But if you did that, would your 27.1 have to be negative as well? Because that's now not del vape, that'd be, or del H of vaporization.
I'm going to come back to that in just a
Okay.
second. What is the temperature going to be? What is the temperature of transition for condensation? It's the boiling point, right? The boiling point's just a number. If you're going from a liquid to a gas, it's the boiling point. If you're going from a gas to a liquid, it's the same temperature, the boiling point. I know it kind of sounds weird, but isn't that the temperature of this transition? Okay, now, what were you saying about this value?
So like the del H of vaporization, you need energy to do it. So it'd be positive. But if you're going from a gas to a liquid, would that delta or del H be negative?
Yeah, right. We're going from, it's the same energy, right? So these are the two energies. This is the energy of the liquid, and this is the energy of the gas. If we're vaporizing it, we're adding that much energy. And if we're condensing it, we're taking away that much energy. So the enthalpy of condensation is just the negative of the enthalpy of vaporization. So that's my point here. You're not going to look up, you're not going to find the enthalpy of condensation in any table. They're going to expect you to know that it's just the opposite sign of the enthalpy of vaporization. Does that make sense to everybody? Okay, so again, do your homework, do your homework, do your homework, do your homework.